Hello, class. Today we have with us a very honorable guest, a man who has made significant contributions to the field of inorganic chemistry, and for his work he has been awarded such prizes as the Priestley Medal, the National Medal of Science, the Harvey Prize, the Wolf Prize in Chemistry, and the Welch Award. So without further ado, let me introduce Harry Gray. Hello, Alex. It's an honor for me to be here. I've been waiting a while to be on your show, and I hope I'm not being too forward, but I must say you're quite the handsome fella. Harry, that's very flattering, but today's not about me, it's about you. So why don't you get us started by telling us how you got interested in chemistry? Well, Alex, as a kid, I was always very intrigued by colors. I wanted to know why the grass was green. I wanted to know why rubies were red. I found gemstones very interesting, but there's something about the colors really fascinated me. And actually, the first color I looked at in the lab was something called Prussian blue. And yeah, it's really what sparked my interest in chemistry. Another little story, when I was 12 years old, I would send letters to chemical companies in Chicago posing as a university professor in order to obtain different forms of acid. I ordered sulfuric acid, nitric acid, hydrochloric acid, and I'd use it I'd pour it on my mom's clothes and just rip them apart. But that was really how I got started in chemistry. Now, from there, you went to Western Kentucky, where you studied chemistry. Yes, as much as I hate to admit it, I got my start in synthetic organic chemistry, making certain organic compounds. But when I graduated and went on to Northwestern University, I was lucky enough to meet Fred Basolo and Ralph Pearson, where they tried to convince me that organic chemistry wasn't going anywhere and inorganic chemistry was undergoing a renaissance and was a booming field. Specifically, they told me I could start to look at colors, and I could start studying the colors of inorganic compounds. And from there I was hooked. I immediately knew what I wanted to do, and I switched my emphasis to inorganic chemistry. So then, after you finished your PhD at Northwestern, you continued pursuing your interest in colors, and why don't you tell us about that? Yes, actually, I went to the University of Copenhagen. I hear the beer is excellent in Copenhagen. Oh, it's some of the best. That's why I chose Copenhagen over studying at Cambridge in England. But anyway, worked with a man named Carl Bellhausen on the crystal field theory, and after a few months in Copenhagen, I realized that crystal field theory was not a quantitatively sufficient way to characterize these metal complexes. It was too simple. It only dealt with point charges. It didn't talk about covalent bonding or molecules. So that was when I started to develop something called the ligand field theory. That's funny you mentioned that. We're actually going to be talking about the ligand field theory pretty soon in our inorganic chem class. Yes, ligand field theory is a nice hybrid of molecular orbital and crystal field theory. It combines the best parts of both of them. It describes the sigma and pi bonding and orbital arrangement of ligands and metal complexes. Actually, it can be used to determine the color of compounds, which was a limitation at the time of crystal field theory. Yes, and after you left Copenhagen, you went to Columbia University. Tell us about some of your work there. Yes, and I was given my tenure there after only a few short weeks, strictly based on my knowledge of platinum chemistry. The lab had just come into contact with about $100,000 worth of platinum, and they had no platinum chemists. So I came in and took a crack at it, and actually published one of my most important papers, the electronic structures and spectral properties of square planar dithioxylate complexes of nickel, palladium, platinum, and gold. You can see here one of the structures we synthesized was platinum dithioxylate, and we also did this with nickel, gold, palladium, And from these assignments, we are now able to place the dithiloxylate planar spectral chemical series and compare its positions with the positions of other biotente ligands. And while you were running your platinum experiments, you were also a professor at Columbia, where you taught your students about ligand field theory, the color of Prussian blue, and if I'm not mistaken, they were the ones who kind of convinced you to apply your knowledge of inorganic chemistry to biological systems, correct? Yes, right. Again, you are, Mr. Reynolds. You're a smart man. I went into the field of biological systems and I started to look at the electronic structure of worm blood to find out why it was like a red-purple. I looked at human blood to figure out why it was deep red. I looked at deep blue proteins, iron and copper proteins. And that was really how I got started into the field. And then, from there, it really exploded and kind of defined part of my career. Yes, and that's, I believe, when you met J.R. Winkler and started to shift your focus more into, yes, like you said earlier, proteins and biological systems, more specifically electron transfer between metal complexes in these proteins. Yes, it was my work with Winkler that helped me win the Priestley Medal, which is the highest award given out by the American Chemical Society. Winkler and I worked on a paper, The Electron Transfer in Ruthenium Modified Proteins. You can see me right here, looking good as ever. And so this paper was about, what we did was we put a probe on ruthenium modified cytochrome C, which you can see right here. If you look closely, you see that little ball here. That's our ruthenium in the whole cytochrome C protein. And what we did was we probed this protein, and we were able to physically observe an electron transfer of about 11 to 15 angstroms, which at the time this is considered a long-range transfer. In most organic chem textbooks, they only mention electron transfers occurring 4 to 5 angstroms short range, but these proteins, complex proteins, were characterized by long-range electron transfers. This was an important paper. It had real-world applications. Electron transfer reactions are vital for life. They support oxidative phosphorylation and photosynthesis. So, this was probably my most noted work. It was important stuff at the time, and research is still continuing in this field. Wow, that is interesting. And if I'm not mistaken, in 1982, you were the first to model electron tunneling through biological media. And I'd really like to reiterate what you said earlier about its importance. This really changed the way scientists looked at electron movement. It was the first time anyone had seen this long-range transfer. Yes, we were the first to model that electron tunneling system, and it really paved the way for hundreds of other experiments that have occurred from 1985 on to today. It was an exciting time in my life, and I'm very proud of the work that Winkler and I did back then. And I've actually got some questions for you, Mr. Reynolds. Why have me on this show? Why'd you pick me out of all the other famous organic chemists? Well, Harry, to be frank, I was scrolling through some photos and I came across yours and I thought, wow, that guy has a funny name and a cheesy smile. But after watching your interview with Richard Eisenberg and seeing your profile on the Caltech page, I saw all the contributions you've made to not just inorganic chemistry, but to biochemistry, to bioinorganics, and I thought it was really interesting how you applied your knowledge of chemistry to outside fields. Please explain. Well, I want to go to PA school after I graduate, and I'd really like to apply my background in chemistry to the medical field. In our class, we talked about neutron capture therapy using boron 10. I'm sure you're well aware of those studies, and I think it would be great if I could mix the two fields somehow. I think that's what learning is all about, is taking knowledge you learn from one area and applying it to another. That sounds fantastic. If I had a PA school, I'd gladly admit you. Hey, there's an idea. Maybe you should start one. I mean, gosh, you've done just about everything else. Oh, stop it. You're too kind. Well, Harry, it looks like we're out of time. I'd like to thank you for taking your time to meet with me today. It was an honor to have you. Thank you, Mr. Reynolds, and best of luck with your future endeavors. I hope I helped you get an A on this project.